Welcome back, everybody, to our lecture 10 in Programming for Data Scientists in Python. Today with the second episode on deep learning. We're right on schedule. After lecture 9, we talked about the machine learning basics and the foundations that we need to understand the more complex deep neural networks. And then we also implement them in a framework called PyTorch that we talked about before. And that's what we're going to do today. So there will be some theory, about 60 minutes or so, and then we'll go into a notebook and we'll actually solve a problem with deep learning, and we'll learn about the different components of PyTorch. So the lecture is more designed to understand what is deep learning, how the networks work, what is the general approach, and this approach and the training and so on, this can be implemented in many ways in Python. And one of the ways is PyTorch. And PyTorch is this most popular framework right now that is based on Python and implements all the different parallelization components that you need and gradient descent and all these things we'll talk about today. But essentially, PyTorch helps you to not re-implement a lot of code when designing neural networks and, not having to do so many things from scratch. Especially it takes away from you how to make it efficient. You can probably implement it in a similar way in Python, but won't be very efficient. So PyTorch is implemented in a lot of C code, C++ code, and CUDA kernels, which are NVIDIA-based kernels that optimize across many thousands of core units that are doing floating point operations at the same time. So those things PyTorch is great for, and that's why we'll use it later in the notebooks. Okay, so again, the recommended literature didn't change. For this lecture specifically, I can recommend the Deep Learning by Ian Goodfellow. The examples we use are just modified versions from this book, so it is very close. If you want to read a bit deeper, that's a great point to start with. And then everything to the right is also great. We didn't use much material from them, but those are great references. So since we talked about this in detail in the last lecture, let's skip this for now. All right, so deep learning, the core component that most networks work with are deep forward networks or deep feedforward networks, and what that means. So first of all, we need to understand how these networks are designed. And basically, they're designed similar to how our brain is designed. So the main motivation for neural networks or deep neural networks comes from the brain. So as you can see on the bottom, a brain cell basically has three main components. And this is a very, very simplified way of talking of brain cells. And I know that there's many researchers from neurology or biology or other fields, psychology, that know much more about the brain cells. But for us computer scientists, we want to keep things simple. So we looked at what are the main components that we can break down. So the main component of the actual cell is the body. So the cell body contains the majority of the information of the cell. And then there's two types of connections. There's the dendrites, which are incoming connections to our brain cell. And these incoming connections get signals from many other brain cells. And then there's the axon of the brain cell, which then outputs information to other brain cells. So since this is a network, we want to have some incoming and outcoming edges. And so on the dendrites, there can be many neurons connected to our neuron or to our brain cell, and they communicate by different neurotransmitters. You might have heard of them. So there's, for example, serotonin, dopamine, adrenaline, and so on. And they have different functions. And also, it is important in which dose they fire these neurotransmitters. So one thing that recreational drugs do, cigarettes, for example, or alcohol, they increase the amount of a neurotransmitter that is passed from one neuron to another. More specifically, they inhibit taking back the neurotransmitter from that dendrite and axon. So the neuron is firing some information in form of neurotransmitters, but they cannot be reabsorbed because a certain recreational drug hinders that. And that's why if people take those recreational drugs, they feel specifically joyful, because there's much more joy information being passed than it should be. So in the regular case, you might be happy if there's something good happening, and it's fine. But if you take these recreational drugs, there's much more of this information coming. So you're hijacking this circuit, so to say. But why do I say that? Is because this weighting of the amount of information that is being passed in form of neurotransmitters is very important to the brain cell, and it uniquely influences that brain cell. So this is something we can also see in the model of a brain cell in deep learning. So here you can see on the left, which we call the weighted sum of inputs, we have x1 to xn being the input neurons to our neuron. So these are other neurons that communicate with our neuron, okay, through the dendrites. So each of these neurons has a connection to our neuron, and they all have specific weights, okay? And these weights represent, or can represent in a way, the amount of neurotransmitter that is being passed from one to another. So in specific scenarios, you might think of this being, okay, we need a lot of information from that neuron because we're in a good situation, so we need a lot of information from that joy neuron. But in other situations, for example, when there's a threat, when you're out in the wild and there's a predator hunting you, then you need a lot more weighting towards your fear receptors or your fear neurons, and they will say, hey, run. So this weighted sum is a representation of how much information from each neuron at specific events should be composed into this current neuron. And each neuron has a different function. We'll see that later. This is true for the human brain. There's certain areas where there's specific functions like language, vision, fear, but they're also interconnected. So they're not like separatable, all of them. But there's certain different types. And if we take the weighted sum of the input neurons and their weights, we come up with a way to say how much influence each neuron gives to the current neuron. And we'll also add a little bias term here. And this is similar to the bias term we've seen in the linear model. This is something to tell our model how to shift from the origin of a function, because now we're not talking biologically anymore, but more mathematically speaking. This weighted sum here will give us any linear function in multidimensional space through the origin, but it will not give us anything that is beyond the origin. So there might be a shift towards one direction or the other, so we might have a certain bias towards a certain situation. So even though the situation might be dangerous, we know that up to this degree it's not dangerous, and that could be the bias. And from there on, our linear function starts to weight these different fear signals, but the bias tells us, okay, up to this threshold, it's fine, and below that or above that, it's not fine anymore. And then we have this linear function, but when should our neuron tell other neurons what to do? And that's where we come to the activation. So there might be signals of the neuron here that come in that are not really relevant. So if this neuron has a specific property, for example, to fire whenever there's threat, there might be different signals that come in, and they're all, they all have some information, but there's no threat. So we don't want to give signal to the next neuron that maybe has the, responsibility to make you run. We don't want that in any situation. So there's an activation on the right side here, and the activation occurs at specific events again. So it shouldn't occur all the time, but at specific events. And here in the simplified way of a perceptron, this could be 0, 1. So stay or run, fight or run, something like this, right? In reality, this can be way more complex, of course, and we'll see later how that looks like. But this is basically the inspiration of a neuron and how it works. So just to recap, we have input neurons, we have weighting of these neurons, which means how important each of them are at specific points. We have the weighted sum, including a bias to offset whenever there's something not passing through the origin in the linear function, and we have an activation that tells us when to fire this neuron. And you can see you can compose many of these neurons into a network, or in deep feedforward networks, into a forward computational graph. So more formally, each of these neural networks can be seen as multiple layers of functions. And we've seen that there's an input layer. This is a specific one because it gets all the information from the beginning. And there's an output layer which gives us the answers. And everything in between we call the hidden layers. And we only specify the behavior of the last layer. We only want to know what happens at the end, and everything else is hidden, so we don't directly specify it. There are specific architectures that specify sometimes in the middle, okay, here should be something happening, but it is difficult because we don't know the answer in the middle of a representation, the same way as we don't know the answer of a human brain cell directly without the human having to have some interaction. So even if we do human studies, most likely we need some interaction from the human at the end. So we have I layers, and that's the depth of the network. So deep learning comes from the number of layers, and we have I layers. And each layer can have j neurons, but you don't have to have the same number of neurons in each layer. So layer 1 could have 10 neurons, layer 2 could have 100, and so on. Usually the number of input neurons is determined by the information we have, and we'll see that in the next slide. And the number of output neurons is determined by the problem. So if we have a classification problem, we'll have the number of classes at outputs. Formally, you can write it as hij is being equal to g, which is an activation function, applied to aij transpose times hi minus 1, which is the previous layer, plus some bias bij. So let's say we have this problem. We have some information about people. We have their age, we have their gender, we have how much sports they do per week, and the number of calories they eat. So those are our independent variables. Those are our inputs, and this is called the input layer. Then we can have multiple layers of hidden layers. In this case, we have one hidden layer, but there could be many more. And each of these input neurons is connected to each of the neurons of the hidden layer. And on all of these edges, there is a weight parameter. So there's weighting occurring between each input and each hidden layer. So each of the hidden neurons has a direct dependency towards the input. And one thing that this neuron could learn is just the correlation of age and gender towards how old people get. So usually, and there's more genders than this, of course, but let's say usually women, cis women, get the oldest. So one correlation that can be learned here is if age is increasing, but gender is female, whatever number that might represent here, 1 or 2 or whatever, the likelihood is higher than if age is high and gender is, for example, male. And other neurons can learn other dependencies, but they all have their chance of learning dependencies from all the inputs. A quick note, this neural network has not very high value yet because one problem that might occur here is the scaling of the numbers. So age is usually up to, let's say, 100, 110 max, but then calories can be all the way up to 5,000 for some bodybuilder. And the same is true for like gender is 0. So the weights here you see have to learn some very high or low scaling in the first layer. That's something we usually don't want to do. So what you can do here, and we'll see that later in lecture 11, you can rescale these inputs. So you can say, I want to rescale them to a standard, to a normal distribution of mean 1 and SCD1. So then all the values lie around 1, with 1, of standard deviation. Or if you want to rescale them all to 0 to 1, what you can do is you can rescale them using min and max. So this way, you always have a value between 0 and 1. There's no right or wrong on this. There's different approaches for different problems. Usually, if you treat this as a some sort of normal distribution, you will not lose or skew the distribution. While with min-max, you will squeeze it to be exactly 0 or 1, and then you might skew the distribution a bit, especially if there's small differences in values for low or high values. You might squeeze or unskew them. And then the last layer, this is our dependent variable. We actually want to have one probability, and that's the probability of someone being alive. So as before, with increasing age, specified by how much sports they do, the probability gets higher or low. So for this example, for someone eating on the appropriate number of calories, doing at least 1 time per week sports, or whatever that parameter means, I don't know, 60 minutes of sports per week, being male, this person has a high probability of being alive. And the output is essentially the dependent variable that we want to train, that we want to get right. And we want the parameters in the hidden layers, or the weights between these layers, to be in a way that they can treat any input and give us that probability. So each layer computes this linear transformation with W as the weights, X as the inputs, and B as the bias. We'll use X as the inputs as a term for inputs in each neuron. We have this bias term that we explained, and then we have a nonlinear activation function, and that is the quintessence of deep learning, if you want. So we'll see later how to train this model, but this is basically the thing that makes them really powerful. So nonlinear activation means you can learn any nonlinear function. If we just look at this term here, we can learn linear functions. But if we apply some nonlinearity to that, the entire network can become a nonlinear function. And the way that I like to see neural networks is they're function approximators. So if you have some complex functions of an input that maps to an output, or independent variables to dependent variables, you try to approximate the function that solves that function, or you try to approximate that function. So some of these nonlinear functions that are really popular are softmax. And what softmax does is, if you have a classification problem and each of the classes are mutually exclusive, and that's just a fancy term for saying that it cannot be two things, it can only be one. That means it can only be a cat, a dog, or a horse. Then this function transforms the output into a probability distribution, which softly, as the name suggests, extracts the maximum of that distribution. So if you have, for example, here you have cat, dog, and horse logits, which are the output of yi, so that's our output layer from before. And you have one value for cat, one for dog, one for horse for each image. You would see that, okay, on the first one, cat got the highest score, and that's great. The softmax actually transforms this to this probability distribution and then gives you still the highest value, but you can also see the other ones got much lower scores. That's the max or softmax operation. So you're probably asking, hey, Jan, why don't we just take the max? And you can do that. The max would also give you here the highest value in all cases. But one thing that softmax does, and we'll see later in gradient descent, is, or two things that it does. First, it makes it differentiable. So you can also differentiate max, but only through one neuron. So if you do max, you cannot differentiate through the other neurons anymore because you disregard them in the max operation. Softmax makes all of them differentiable, so we can also propagate back through the values that were not good, not just the ones that were good. So we give feedback not only on cat, but also on dog and horse. And the function is pretty simple. You take e to the power of yi, which is the current neuron, here 5, by the sum of all e to the power j, yj. So this is the sum of e to the power of all of them. And that gives you the score. And it will always sum up to 1. If you have a problem that is binary in nature or non-mutually exclusive, meaning that, for example, we don't have cat, dog, horse, but we have cat, small cat, and white cat, so it can be all of them. It can also be none of them. That's where the sigmoid function comes in. And the sigmoid transforms any neuron into 0 to 1. And you don't have to have information about the other neurons like in softmax. And you just take 1 over 1 plus e to the minus yi, and it will transform into that score. So now we treat each neuron independently. Usually it's for binary problems, but you can also use it for multi-class problems. And yeah, so that's another function. And there's many more, as you can see here. So a pretty old one is 10H. Then ReLU is something we look today. There's variations of ReLU that are being used, but there's many activation functions. Usually you use some kind of function that transforms into probability distribution for classification problems. Softmax is probably the most used one in classification problems. Also because there's a trick how to make it the negative log likelihood, as we've seen in lecture 9. And ReLU is, or some variation of ReLU, is the most used function for hidden layers. Okay, so let's learn our first problem with deep networks. And that's actually a simple problem, the XOR problem. If you remember in lecture 9, we have talked about this perceptron that was introduced and this book about perceptrons that are basically looking at how well they can solve problems. And this problem, which is actually very simple for humans and also very simple for different programming languages, is quite complicated to do in perceptrons. So let's start with giving some examples. Most of you probably know this, but I just want to make sure everyone's on the same page. So logical operations are just operations between binary values in this case. So you have 0 or 1. x1 and x2 can be 0 or 1. So there's 4 combinations. You can have 0, 0, 0, 1, 1, 0, or 1, 1. That's all the combinations that are there. And the OR operation is saying that if there's one value that is 1, then the OR operation returns 1. And you can read it like this. If the first one is true or the other one is true, it is true. Okay, so if the first one is false, okay, we look into the other one and the other one is true, it is true. So this can actually be learned with a linear classifier from the last lecture. So you can actually say that it is class 1 whenever wt times x, which is our parameter for the slope, is greater than w0. And that is true for wt being 1, 1, and then w0 being minus 0.5, and then minus w0 being 0.5. And then you have this slope. Everything that is above this threshold is 1, is class 1. Everything below is class 0. So, and we can check if that's true. If one parameter is 1, it is 1. And if both are 1, it is also 1. Only if both are 0, it is 0. And if you use the AND operator, that's pretty similar. Now we just swap it around. We read it like, if one is true and the other is true, then we return true. If one is false and the other is true, we don't return true. If both are false, same thing. So here we just swapped it to only be 1 if both are 1. Again, can learn this with a classifier in a linear way. We just move the threshold up here, and then we can also classify it the same way. So this seems really easy, right? What if we take another operator that looks like this, XOR? In this case, we only return 1 if one of the values is 1, but not if both. So it is 1 in 2 cases where one of the values is 1 and the other one is 0. If both are 0 or both are 1, this is 0. So if we take the line from before, we can use any slope and any offset, okay? So if you try to fit any line here in any way, any slope and any offset, you won't be able to find one that satisfies this condition. What you could do is probably to learn some nonlinear function. If you try to go all the way down here and then go all the way down here, or you try to first get this one right, and then go this one right. Actually, this is not so easy to learn with a polynomial too. So it is quite difficult to find a boundary here. Maybe some slope that captures this, and then a slope that captures this. And this is highly nonlinear, actually. So if you try to do that with a linear function, it doesn't work. And even with polynomials, you have to think a bit. It's not impossible, but you have to think about it. And one way we can solve it is neural networks. So, and actually a quite small neural network. We only have 2 hidden neurons. So the input neurons are given, right? We have x1 and x2. Those are our inputs. We cannot change that. We want to find out if x1 and x2 in some operation give some value. And that's why also the output is defined. This is our XOR value. So if we do that with a neural network, we can use the ReLU function for activating the hidden layer. And this looks like that. So we have a training set of all the different examples that we just looked at. We have 0, 0, 0, 1, 1, 0, and 1, 1. And we have, this is from here, this is this table. And we also have the outputs, which are 0, 1, 1, 0. So we have one matrix of training examples and a vector of output examples. And we can define a very easy weight matrix of all being 1 and the bias of being 0 and -1 in the first layer here, in the hidden layer. And then for the output layer, we define the weight matrix as being 1, -2, and the bias to be 0. And now we can compute that. So if we take the first layer, we compute the training set X times W, and that gives us this matrix here. If we add a bias to that, so the bias is 2 values, it's added to each of the rows of our data set, we receive this matrix. And if we apply ReLU, ReLU just is the maximum of 0 and Z. We take all the negative values and make them 0. And that's it. Everything else remains the same. And we get this matrix. And now we apply the last layer. We take the matrix from before. This is the same matrix as the last slide. So here, 0, 0, 1, 0, 1, 0, 2, 1. It's the same here. And we just multiply it times W, and we get this vector 0, 1, 1, 0. Remember, we don't have a bias on this one here. So 0, 1, 1, 0 looks exactly what we had on the XOR, right? So here, 0, 1, 1, 0 is the solution for our problem. So we have found a solution using the neural network. The important question is, how do I come up with these weights? So how did I get them? I cannot just say those are the weights and this is the solution, right? We need to find out what are the weights. And we can do this analytically, but that's very complicated. So we want to have some sort of algorithm that solves it for us. So especially for large problems and complex problems, we want to describe how well is the model answering the question. So if this is saying 1, 0, 0, 1, this is exactly the opposite of what we want. So the model is describing the solution very badly. If only one of them is off, we can say it's describing it 75% right, and so on. So we want to come up with a loss or error function, similar to the one that we had in the last lecture, which describes how well are we doing. And then we want to decrease this function in a similar way that we had before, but more generalized using gradient-based learning, and then backpropagation, which means we want to backpropagate all the weights through the network. So that's where we come to backpropagation and gradient descent, which is the most used algorithm, or the used algorithm for deep learning. And the goal is to minimize this loss function. And now how do we compute it for each layer? First of all, the network is the same. We just, instead of the values, we put the weights here. So on top, this is the layer 1, layer 2, and then this is from input node 1 to hidden node 1, input node 1 to hidden node 2, and so on. Our prediction is y, and that should be the XOR. And then we have y hat, which is the actual true value from our table. And then we have a loss function. And that function tells us how good the prediction is in accordance to the label. So to minimize the loss function, first we take a random guess for the parameters. And that means we're initializing the network with a random guess for the parameters. For example, some normal distribution, and we can put the layer size in accordance to that. There's some regularization terms to do that, but basically it's just randomly initialized according to some normal distribution around 0. And then we want to optimize each of the weights by the opposite sign of the derivative of the loss function. So what does that mean? Let's say the loss function is this blue line, okay? If our parameter x is moving too much to the right or to the left, the loss function is higher. So our optimum is x being 0. If we want to decrease that loss function at any point, we can compute the derivative, which tells us what is the slope at each point of the loss function. So if we're here, x being greater than 0, then we have f prime x being greater than 0. And that means that the gradient or the derivative is greater than 0, and we want to move it to be 0 here. So we take the opposite sign of that derivative. And we can see an example on the next slide. It's probably easier to understand. But what we do is we take the current weight, we define the next weight that we optimize to be the current weight minus some learning rate times the gradient of the loss according to that weight. And the gradient of the loss according to that weight means how much we're moving in that direction. The learning rate just defines how much we should move. If we move too much, we might overshoot and come to this other side, and then it's like a ping pong game. So it should be small but steady moving down this line. There's a really cool animation by 3 Blue 1 Brown. It's a YouTube channel creator. I linked him here, where they show this. So at any position, you can compute with this line the derivative, and then we move into that opposite direction of the derivative. You see, we're using small steps to move into the steepest direction to optimize the weight so that the loss function decreases. So, and how do we compute these gradients? The gradient of the loss function according to some weight of the first layer might be complicated because we have many layers, and that's where the chain rule comes in. All of these layers are just functions of each other's. Remember one of the first slides? It's just an encapsulation, f of g of x, or h1 of h2 of h3 of x. And we can use that definition of functions inside functions to use the chain rule in derivatives. So if we want to compute the gradients of each of them, it's df by dg of g times dg by dx of x, and that's the derivative of the chain function. And you can also do that in a multivariate way, and we'll see that in more detail in the next one. So let's take a very easy neural network. You have one input neuron, one hidden neuron, and one loss function. And the hidden neuron just computes the square of the input, and the loss function is just 2 times the hidden. So we can say a forward pass is how we compute the output y of the model. We just take x squared. That's the forward pass. Just compute x squared. And to compute the loss, we just take 2y, which if we take the forward pass is 2x squared. And that's great. So to compute the gradient, what we have to do now on the backward pass, and that's our backpropagation, we have to find the derivative of L according to x. So the first thing we do is we compute the loss in accordance to y. And that's basically the loss by the loss, which is 1, times the loss by y, which is then 2, because the derivative of 2y according to y is 2, right? Because then y transforms to 1, and we just leave there with a 2. The next step is to go back to the weight, to the input. So that's where we do now dl by dx. This should be, of course, a small x. And that's dl by dy. And we computed that in the first step or in the second step. And then dy by dx. And that's basically nothing else than dl by dy times 2x, because the derivative of dy to dx, according to x, is, so x squared, the derivative is 2x, right? So we can actually compute that, and we'll get the loss. So let's go one step back. The loss over the loss is 1. The loss by y, we said, is 2. And then the loss by x is 4x, because we take the 1 times the 2 times the 2x that we just computed. And that's how we got the gradients for each of these different stages. We take the chain rule, we compute the gradients of each step, and we then just multiply them in their accordant position. So most of the deep learning frameworks, and PyTorch is one of them, implement automatic differentiation. So at each step the neuron knows what is my gradient with respect to the inputs, what is my forward value, and then you can compose arbitrary chains of many, many thousands or millions of neurons. But each of them just has to remember what their gradient and their forward value is. And they're all computed by chain rule, but they just have to do one operation, basically. They just have to do one operation in accordance to the previous layer. So each neuron has the dependence of the previous. And then since the previous has the dependence of that previous, we have a chain that is then computed after each other's. So there's many parts that can be parallelized in the neural network, but you cannot parallelize many operations between layers. So there's some information that needs to be computed then when knowing both layers operations. So how do we train these things now? And there's a simple training loop that we basically use in all of these networks. So we initialize the weights by some normal distribution, and there's many different ways to initialize. That's just one way to do it. It's just our random guess from before. And then we have something called an epoch, and an epoch is the entire training set. So if you have 1,000 examples of images, that's the 1,000 examples. If you have 50 books, that's the 50 books. And within that epoch, we iterate over the training examples. Usually we do that in something that is called a batch, but in its most simplest form, we just iterate over each training example. And we compute the forward pass, which is applying the function of the neural network. This is usually really fast because we just have to multiply the weights times the inputs and so on. And then we compute the backward pass, which in this case here is computing the loss and then the gradients. So here should be probably the gradients too. This is a mistake. And then we perform an optimization step. So the optimization step in the classical gradient descent algorithm would be indented here on the left. So you have all the training examples, iterate over them, compute all the gradients, and then do one step of the gradients. That's not very efficient, especially if you have a lot of data, because then you update only in every, 1 million operations. So that's why we indented it here. If you have batches or individual examples, you would do a step every time. So every time you do an estimate, and that's also referred to as stochastic gradient descent sometimes. The stochastic part comes by not having the gradients of all the different training examples, but just a sample of them. And that's usually a good thing, and we will talk later about why that is. So one problem that occurs with these gradient-based methods is that you have to have some high enough derivative to be able to change those weights. So if we take the sigmoid function from before, the derivatives are here in the red line. They're really low for most of the times. So if the values are high, and you can see that the slope is really low, the derivatives are low. So on the cases where we probably need more changes, the derivatives are quite low, which means that if you are trying to optimize a network with many layers on sigmoid, you can see that the derivative here is maybe 0.25. If you propagate that one layer below that, it would already be 0.25 times 0.25, which is much lower than that. So the initial layers at the first positions, they have no chance to optimize efficiently. So one of the solutions is to use something like the ReLU activation, and we've seen that in the example. So the ReLU is nonlinear because it's a max operation. So here it is not linear. Or sorry, here it is linear, but in this point it's not linear. And all the rest is linear, which means if you compute the gradients, it's exactly 1 for here for the positive values. So if you backpropagate this many layers, the gradient won't get diminished or get smaller. So let's go back to the XOR example. Now we want to learn it with gradient descent. So let's see, here we have a forward pass. So there's x1, x2, the same way. We call the hidden layers now u and v. Prediction is still y and labels y hat. we have the loss function. So now we can say u computes a function of x1 and x2, v computes a function of x1 and x2, and y computes a function of u and v. And then the loss is just this monster here, which is taking y is taking u and v, and they're both dependent of x1 and x2. And here's actually a closing bracket missing. And this is compared to y hat. So if we go back, we do the same thing. We compute the loss independence of y. We don't compute the loss independence of y hat. Why? Because there's nothing to optimize. The label is just given, and we don't have to compute anything there. So we go the same way back, and we compute y independence of u and v. So the derivative of the loss of u is the derivative of the loss of y. This is the first part of the chain, times the derivative of y to u. This is the second part of the chain. And the same thing we do for v. The loss independence of v is the loss first of independence of y, and then y independence of v. And now we can compute basically any input of the neural network x1 and x2. So if we want to do something for x1, we go the way back from u and v. And those are two gradients that are coming from x1 because they're both connected to u and v. So we take the loss independence of y times y independence of u. So we take the upper road times u independence of x1. So we go all the way top, top, top. And then there's another part from the bottom. First, we have to go the loss independence of y, then y independence of v, and then v independence of x1. And since there are two incoming gradients, we have to sum them up, right? Because there's two parts of what makes those weights here. So the loss independence of x1 is the sum loss of both of them. So here, each of these weights can be computed together, but the gradient for x1 independent of the loss is the sum of both of these routes here, or each of the individual routes here. So we can implement this in a fairly straightforward way by assigning each of these nodes, or each of these nodes is an object, and each of these objects has attributes for value and gradient. And the values represent the forward pass, the actual value that is computed, and the gradient represent the backward pass that we just computed. So here we can say that x value is just the input value, the u value is the function of x1 and x2 values, the v value is function of x1 and x2 values as well, the y is function of u and v values, and the loss is function of y and y hat values. And on the backward pass, we can initialize all of the gradients being 0, and usually you do that in each training loop. And then you can say that the loss gradient is being 1 in the beginning. And you compute then each of these steps that we did before by saying that the y gradient is gets added the loss gradient times the derivative of the loss in correspondent of y, given y value and x hat value. And you can do that for each part of the network, and therefore you get the gradient of each node of the network. And these nodes are basically, the weights that we want to compute in the end. So yeah, you can define this as functions of the other parts, and as you can see, when you compute one of them, you can compute the next one of them. So you just in each step have to compute the direct predecessor of the neuron. So here you have to compute that one function where you derive u independence of x1, and you add that to the gradient of that x1. So that was a quick lecture, but we will have more to go through in actually PyTorch, which is why we're going to the code right now. I hope you enjoyed this lecture, and we'll meet you in the notebook in Python. Thanks.